Start working on your electrochemical cell sheets. So we started here, right? So we're starting to see a connection that this E cell is going to be closely related to delta G, right? And this E cell is, we talked about potentials and all that. This is standard cell potential. It gets confusing as well because potential is used differently than standard electrical potential because this is a cell potential. And so the cell potential is not just related to the movement of electrons, but also it's related to a thermodynamic quantity, right? And so the same way we think about equilibrium, if you change concentration of a reactant or product, Le Chatelier's principle will shift the equilibrium accordingly, right? So the cell potential is in a way related to that. It's saying which side is more likely to be reduced, right? That's the higher cell potential, that's at the cathode, and that's how we define the cathode. And this is because it's saying that reaction has a stronger pull for electrons because it's more likely to be reduced. It's the strength of that reaction that pushes the reaction in that direction, right? It says how likely are you going to be reduced? And then vice versa, whichever one has the smaller reduction potential is saying that, this side is not as likely to be reduced. So this is where oxidation is going to occur, and that's the anode. Analogously, that means it's the same thing as, potential energy, which is related to minus Q times the change in electrical potential. And this is where we lower our potential energy, right? So we lower our potential energy by going to the negative value potential anode to the positively valued potential cathode, right? So this is our definition from physics. And they're done simultaneously, but the driving force for what pushes electrons towards the cathode is the fact that at the cathode, that's where the reduction reaction happens. If you have a larger value for the reduction potential there, that means that you're more likely to do reduction at that spot. So that reaction is what's driving electrons to moving there. But at the same time, that means physically there also has to be a lowering of the actual potential energy of the electron. And that's related to the potential difference between the cell, right? So I know there's a lot of different things going on here, right? There's a change in the lowering of the potential energy, but you're moving towards the higher cell potential because that's describing how likely the reduction reaction is going to happen, right? So you're moving towards the larger cell potential at the cathode, and you're going to a positive value of the electrical potential, going from at the anode a smaller value of the reduction potential, because you're saying the smaller value of the reduction potential means reduction is less likely to occur there. So it's like a chemical imbalance in equilibrium. It's the chemical reaction that's driving things moving towards the cathode. And this is also going from a large negative value of the the electrical potential, which is like rolling down a hill, towards a positive value. So it can be seen both ways. It can be seen as moving towards this place where, so this is like a thermodynamic quantity, moving towards a place where reduction is more likely to happen, right? That's the thermodynamic thought process behind here. Physically, we also know that means we're moving from a negative electrical potential to a positive electrical potential. And the reason for that is just because charges are negatively valued. That's why we're going from negative to positive. So physically, we're lowering our potential energy because we're going from something negative to something positive, or more positive, right? Just like with the, when we're looking at these cell potentials, when we go to something super negative to something less negative, that's also moving in the direction of something negative to something positive, right? So if you go from a larger negative value to a smaller negative value, right? The same way we look at the oxidation number, right? That would still be a reduction, even though we're still at a positive value, right? If we go from positive 7 to positive 2, we're still at a positive value, but we've still gained electrical charge. We've still gone to a smaller positive value. So it's the same idea here. The signs are flipped because electrical charges are negative, but we're going from a negative larger value to a more positive value, which means we're lowering our potential energy, right? So this is lowering the potential energy which is U, right? This is what we look at in physics. We're lowering our potential energy in this process. This is thermodynamically moving towards the electrode where a reduction is more likely to occur. Towards electrode where reduction is more likely to occur. Right? The same way, if I lower the concentration of a product, you move towards equilibrium because you want to make more of that product to keep the equilibrium constant the same. Here, we've measured something called the standard cell potential, and we're saying we're moving towards a direction where reduction is more likely to occur, right? If we have a current carrying wire, we look at our half reactions, it's like you're pulling electrons from one side, which means that the reaction will move to add electrons to that side, right? So that's the thermodynamic thought process, is the cell potential, and it's also seen as lowering the total potential of the electron in this case, right? The electron experiences a lowering of potential, and it's also driven in that direction because of it's moving the side where reduction is more likely to occur. So I'll let you guys finish writing that, and then I'll go. And so, the potential energy difference represents the maximum amount of work that can be done in the system, right? So the maximum work, the same way that we define, does anyone know what work is defined as in mechanics? If you remember from either a previous physics course or high school or something. In a very simple way, work is defined as the force times the distance you've moved, right? The force you've applied over the distance you move equals a unit of work, right? And work is measured in units of what? Joules, right? And joules are kilogram meters squared per second squared, right? So a Newton is a kilogram meters per second squared times a meter, which is a distance, so that gives us kilograms meters squared per second squared, which equals a joule. In a electrical system, the work is defined as minus the charge times the change in potential that the electron experiences, right? Potential is given in joules per unit coulomb, and so here you get how those two things cancel out. And so in our cell, our standard electrochemical cell, or in our electrochemical cell, this is also then going to be because of the realization that we're moving towards higher reduction potential, right? Because that's where we're more likely to be reduced. This is also going to be related to then the standard cell potential of the electrochemical cell, right? We're lowering the potential energy of the electron, that's what it's experiencing, and it's also being driven there because it's moving towards the sides where it's more likely to be reduced. Bless you, right? So the change in potential is related to the standard cell potential, right? These two things are simultaneously happening. Doesn't mean the They're going to be measured in exactly the same units, but they can be converted to one another usually. And we can replace this then with minus Q times the standard cell potential. Right, and this is the maximum work that's available to do to the system, right? Moving a single electron from one electrode to the other is the maximum work you can do because that's the movement of the electron. That work is also represented in the chemical reaction, but the energy that you've gained or lost in the chemical reaction is put into the movement of that electron, right? You're saying the thermodynamic quantity of the chemical reaction, the free energy or the energy movement of the system, is equal to moving one electron up from the reduction side or the oxidation side to the reduction side, right? You're saying those two things have to be related and they're similar to each other. But as often in chemistry, we don't deal with single electron movements, right? We're looking at vast numbers of these reactions happening, right? We can then define a constant that we call Faraday's constant, which is 96,485 joules per 1 mole electron. You get this because the Coulomb charge is 1.19 times 10 to the 19 minus 19 coulombs per 1 electron. We get Faraday's constant because we can just convert that from the charge per 1 electron to the charge per mole of electrons. How do we go from a single electron to a mole of electrons? What do we use to go between moles and numbers of things? Avogadro's number, right? And so this would be 6.022 times 10 to the 23 electrons per 1 mole of electrons. And if you go through and calculate that, you see they're about 4 orders of magnitude different. That's why you get a number around 10 to the 4, right? That's where we get this value for Faraday's constant. Because now we're looking at not just movement of a single electron, but a mole of electrons. And so this, we can then say, well, the maximum work, we're still writing? Can I move on? You good? I saw you still writing, so that's fine. Good? Okay. So the maximum work, then moving a mole of electrons, right? We would say that this is just happening a mole times, would be then the number of electrons or the number of moles of electrons times Faraday's constant. And the number of moles of electrons would be the stoichiometric amount in your half reaction or the total amount of electrons transferred times Faraday's constant times the standard cell potential, right? So this is the max for a number of moles of electrons. And I meant to write this down here. This is minus N F E cell. And what was supposed to go up here was that the charge is equal to N times F, right? The total charge that you're moving is the number of moles of electrons times Faraday's constant for a large number of electrons. All right, this is the total charge of moving a large number of electrons. So now our standard cell potential, we'll see, will then be in units of joules per mole, right? And so that's how we're going to be using this. And so we briefly mentioned it in our talk about thermodynamics, but this maximum work is also how we define the Gibbs free energy of a system, right? So the Gibbs free energy is the maximum available amount of work that that system can do. And in a simple way, like in a maybe a more intuitive way, if we're just thinking about temperature, this is basically the temperature exchange with the surroundings for a system, right? And that's related to the entropy change of the universe. Or if we think about, the maximum available work that you can do for a system is just, if you have a cold and a hot side, would be the difference in heat exchange with both of those sides. That work is just represented as a exchange of heat with the system. And that's because that's related to the entropy change of the universe, right? When the heat in the system and the heat of the surroundings exchange with each other, that gives you an overall result in the change of entropy of the universe, which tells you about the spontaneity, which we know is related to the Gibbs free energy times the temperature. So this is defined as the maximum amount of work that the system can do. And we also know that delta G has a million other definitions, right? It's also related to the equilibrium constant, and it's also related to concentrations, changes in pressures, and all these things. So because we know that it's equal to the maximum amount of work that the system can do, it's also equal to, now the new thing that we've shown, the number of moles of electrons transferred in the overall equation times Faraday's constant times the standard cell potential. All right, and this is the standard Gibbs free energy for this reaction. And so now we can connect delta G and equilibrium to our understanding of redox reactions. So delta G we know is minus N times Faraday's constant times the standard cell potential. And we also know delta G for a reaction, right? So we know it's related to the standard cell potential for this, electrochemical system. But it's also a chemical reaction, right? The system is a redox reaction happening. We also know that delta G for any reaction is also related to the equilibrium constant of that reaction. So the equilibrium constant, this is one way we can define the system in terms of concentrations of the system. And we also know it's related to this, thermodynamic idea that the cells are going to move, or the electrons are going to move to the side of the electrochemical cell where reduction is more likely to occur. And so when we combine both of these, we get NF E cell is equal to RT ln K. Which means that if you solve this for the electrochemical cell, we can divide both sides by N times the Faraday constant. I already got rid of both the negative signs on both sides of the reaction. What happens to NF, or the number of moles of electron, times Faraday's constant on the right side? On the left side here. They cancel out, right? These cancel out with each other. Oops, I did that on the wrong side. These cancel out with each other. And we get that the standard cell potential is also related to the equilibrium constant of the reaction, scaled by this RT, which is the thermal energy of the system, over the number of moles and Faraday's constant, right? So that scaled by the energy that's stored in the number of electrons that are present times the equilibrium constant, right? So now we have a relationship between the standard cell potential and the equilibrium constant for our redox reaction, right? This here is our equilibrium constant for the redox reaction itself. So when we're writing our overall redox equations with water and hydrogen ions or hydroxide ions, this is the equilibrium constant for that process. Oops, back, sorry. Is anyone still writing? So we can simplify this if we combine all our constants. So this is at 25 degrees Celsius, so at room temperature, if we're looking at change. They used a logarithm, or I used a logarithm. You can convert this. If it was a natural log, it would just be 0.0257 ln K over the number of moles of electrons. All right, so all they did is they just combined 0.0592 is equal to RT, where that's 25 degrees Celsius, log the number E over Faraday's constant, right? So look, R is a constant, that's our ideal gas constant. Faraday's constant is a constant. Temperature is given to you, and when you go between log and natural logarithm, that's how you get this value right here. And now we have a relationship between delta G, the standard cell potential, delta G, the equilibrium constant, which is related to what you guys did in the lab when you looked at solubility, and also now the standard cell potential and the equilibrium constant. All right, so standard cell potential is related to the electrical potential that electrons experience. That's related to thermodynamic driving forces that say either reduction or oxidation is more likely to occur, and electrons move to that. And then both of those are related to, if you have different concentrations of your reduced and oxidized aqueous species, that also shifts the direction of equilibrium. And all of those should be consistent with each other, right? The standard cell potential, electrons should move to the side where reduction is more likely to occur. That means that the concentration of the reduced ions in aqueous solution should go down in accordance with the equilibrium constant, which is also then saying that the potential energy of the electrons should be lowered when they go from the anode to the cathode, right? So all of those three things should be consistent with each other, and they are. Right here, we're looking at concentrations of reactants and products determines that ratio, K, right? That's what we know from equilibrium. We're saying that here the electrons should lower potential energy on that side of the reaction, right? They should physically lower their potential energy, and that is correspondent with the idea that they are moving to the side where they're more likely to be reduced. That's the thermodynamic understanding of that. And then the last relationship is saying, well, these things have to be consistent now. The standard cell potential should also tell us the direction this reaction is going to move. Okay, so I'm going to skip ahead a little bit. If we have a non-standard state system, right? So this gives us relationships. So whenever we see the little degree symbol, like delta H, delta S, delta G, that little degree symbol just means in the standard state. And the way we analyze this is because in the standard state, it allows us to derive a lot of these relationships. And that's because our thermodynamic functions are path independent. So it doesn't matter how we get from point A to point B. We can analyze things in the standard state for the complicated stuff. And then for the various changes in pressures and concentrations, we can then treat those separately from each other, right? So if you're looking at a reaction happening at a non-standard temperature, pressure, or condition, then you can treat each of those processes separately. So if you have a system that doesn't happen at standard temperature, pressure, or in this case, varying concentration, right? The direction a reaction moves, if you were given the equilibrium constant and non-equilibrium concentration, what did that depend on? How did you determine, if you had non-equilibrium concentrations and an equilibrium constant, the direction of movement for that reaction?
The reaction quotient?
It was Q, the reaction quotient, right? The reaction quotient tells you the direction, and you compare that to K, tells you the direction the reaction moves. And for delta G, what that means is if we have a non-standard Gibbs free energy, we can analyze the delta G at standard conditions, right? That's something easy for us to understand. And we get another term that's then related to these non-standard conditions. So we get RT, ln, Q, which is our non-standard state concentrations, right? So now we're not at 1 molar anymore. We're at whatever our initial concentrations of are the system. And we're saying that that now affects the overall change in Gibbs free energy. We change from the non-standard concentrations to the standard state, and then we look at the reaction or whatever process happening at the standard state, right? So this is the standard state change. And this is the non-standard state change. And this is because delta G is a state function. Right? We can analyze it. What is the standard state change? And then whatever that change is, we just add to, well, what is the change from standard state to non-standard state? Right? So we don't have to look at, well, how do we treat the standard cell potential at weird pressures and weird concentrations? Well, we know how it works at standard state because those are what our values are tabulated for. And we know how delta G changes with concentration. We know how delta G changes with pressure, right? We'll just treat those in another step and look at just the reaction happening at standard state. And so we can substitute our relationship for E cell equals, what is it? Sorry, NF. And F E cell equals delta G, and sorry, this is plus RT for a standard state. We can plug that in for all of our expressions for delta G, and we get the non-standard cell potential is equal to the standard cell potential minus RT over NF ln Q. All right, so if you just, wherever delta G is, you just substitute this relationship. We also have minus NF E cell equals just delta G non-standard state. You sub both those in, and you just get rid of the NF values in front of the cell. You get this relationship here. So this tells us how the standard cell potential changes under non-standard state concentrations. And Q is looking at the overall redox reaction, right? Q is looking at our overall reaction for the redox system. So if you're given an electrochemical cell, you can write the full reaction and use that to calculate Q. And so this is what's called the Nernst equation. And the Nernst equation is still really important for modern electrochemistry. All right, so I'm just going to discuss one last thing here. Oh wait, did I give you guys the right? Where was it? And so, what is this, electrolytic cell? Where did I? Cell potential. I feel like I'm missing. All right, whatever. So this allows us to solve for the standard cell potential at non-standard conditions, right? Or the cell potential at non-standard conditions, because this is just another step that we treat in another thermodynamic path, right? So we're taking two easy steps instead of one complicated step to get from reactants to products, and so on and so forth. And so the electrolytic cell, so I think I lost a slide. Right. You can be asked, another form of the question is how many grams of something will be deposited if we are given a certain reaction. If you're given a certain reaction and you run a certain current through that reaction. Right, so if you have a current is given, does anyone know what the units for current are? Ampere, right? Which is A, is amperes. And an ampere represent a coulomb per second, right? So it's C per S. Those are what the units of A are, right? It's basically how much charge are you moving per second. It's kind of like a velocity, except in distance, you're looking at charge moving per second. And so if you're running a current through an electrolytic cell, we talked about, well, this can drive some plating, electrochemical plating reactions, right? You have a non-spontaneous process that can then drive stuff to go from the aqueous phase. It can be reduced to then plate one of your electrodes. If you're given an amount of grams, you can use unit conversions and amperes to then get the amount or the time it would take to get that amount to be deposited, or vice versa, right? If you're given the time, if you run it for a number of hours, how many grams can you get? And so if you're given the grams of a certain metal, you can first convert this into moles, right? So you're given grams of metal. You can convert that into moles of metal. And how do you go from grams to moles? Molar mass, right? So you divide by the molar mass value, molar mass in grams per 1 mole metal. And then you can go from moles of metals to moles of electrons, right? How do you know what the mole of metal to mole of electrons are? Avogadro's number is when we go between moles and specific numbers of electrons. But first we're going to go from moles to moles of electrons. So when you convert from moles to moles, what do you usually use? The molar ratio, right? You use molar ratio to go between them, right? So if you use the moles of metals, that gives you the moles of electron, and this comes from, so this is, we go to the mole of electrons, this comes from the molar ratio. And this comes from our balanced redox reaction. Right? Our balanced redox reaction tells us for how many moles of aluminum do we make, for example, we get 15 moles of hydrogen or electrons transferred. Right? So this gives us from our balanced redox reaction. Then once we have the moles of electron, we need to look at converting that to charge. How do we convert the moles of electrons to the total charge of electrons? Right, did we look at any other constants here that were in units of charge per mole or anything?
Oh,
Faraday's constant, right? So then you use Faraday's constant to go from moles of electron to charge, right? So 1 mole of electron is 96,485 coulombs, right? This was the charge of 1 mole of electrons. It's a relatively large charge value. And then if we want to go to our final thing, which would be the time it takes to deposit that many coulombs, what would we use to convert between those two? All right, we want to go from coulombs to seconds. What value would we use there? Right, we would have to use the current that's being driven through the system, right? Because the amperes is given in units of current per second. So if you divide by the current, you'll end up with units of seconds, right? So if you're driving a electrolytic cell, right, this is a non-spontaneous process to deposit metal on one of your electrodes, you need to run it for a certain amount of time to get a specific number of grams of that metal, right? And so if you were given an arbitrary reaction and you didn't know what the moles of electrons were for the redox process, you could measure something like the standard cell potential of that reaction, use that to determine the moles of electrons that have been transferred completely, and then use that to then either determine, if you're given a certain current, how many grams will you produce, or if you want a certain number of grams, how much time you're going to need to run that current for. Right? If you're given a certain time that a process happens, you can determine the number of grams, and if you're given a target amount of grams, how long do you need to run that process for? Right? So this is combining now unit conversions with, and the reason I'm just going over this is because there's one on the worksheet where you're asked to find how many grams of something will be deposited. Well, it's related to our electrochemical system, but it's usually just unit conversions is how we do that. It's not a terribly difficult problem. Okay, so just to summarize, we have a relationship now between delta G, the equilibrium constant, and the standard cell potential, or the regular cell potential. We then also have our half reactions that determine the direction, or what is our cathode and what is our anode for our system, and we know how to balance them in various acidic or basic solutions. All right, so usually we spend a good amount of time going over problems, but we'll use the lab time to go over this worksheet, which is essentially a lot of the problems that we would go over. All right, so any questions on that before we're done with electrochemistry? All right, so you guys can go ahead and start working on your dry lab. I'll go around and help you guys. If you didn't pick up a dry lab and you want it, it's on Canvas, but there are copies up here. But if you come and get a copy up here, just make sure you get 2 at a time, right? Because they didn't have staples in the copy machine downstairs. So it's 2 different sheets that go together.